Hello, audience. In class, we covered a Turing machine with one tape, but as functions we computed with it got more complicated, the machine got complicated even more, and computation with it was very, very tedious. So I'm gonna show you some enhancements we can do to our Turing machine to make it user-friendly, and then I'm gonna show you some other computational model that is different from Turing machine. First big enhancement we can do to make computation with Turing machine easier is we can add more tapes. So on the left side we have a machine with one tape, and on the right side we have a machine with k tapes. As you can see in function delta, a gamma has k in exponent next to it, meaning we have k tapes to read, and we have k tapes to write to. And one more thing we can do to make working with multiple tapes easier is we have this S over here. Means that we don't have to move all the tapes every time. We can work on one tape and make other tapes idle, meaning stay at the same spot until we need them later. So let's look at the example. This is an example of counting with three tapes. So over here you can see that if we see 1 on the first tape, we move right, meaning we advance our input, and we engage our second tape to record a number of ones. So this flowchart is for counting in binary. I did it to save space because every time you see 0, you replace it with 1. And if you wanted to make it with decimal, you have to replace 0 with 1, 1 and 2, 1 with 2, 2 with 3, and so on. So I just did this one in binary to make it easier to read. And over here, when on our first tape we encounter 0, we engage our third tape to record number of zeros. And as we reach the end, the blank symbol, we accept, we hold and accept. So let's look at the example. I mean, that was an example of flowchart for a three-tape Turing machine. So this is exactly the Turing machine I just showed you in the flowchart. It has three tapes. First tape holds an input, and it's gonna count number of zeros on the third tape and number of ones on the second tape. So let's run it. So as you can see, head of the first tape always moves forward, and heads of the second and third tape move back and forth, replacing digits to record correct number of 0 and 1 that are read from the input. Okay, so it's not much longer. Let it finish. Okay, and it holds. So it counted 34 ones and 35 zeros. Okay, so it works. So you might think that if we have more than one tape, the Turing machine becomes more powerful, but it's not. All Turing machines are equivalent, meaning that for every operation we perform on any Turing machine, we can build a Turing machine with only one tape that does exactly the same thing. Okay, so here's an example of a Turing machine with one tape that does exactly the same thing as the previous Turing machine with three tapes did. As you can see, this flowchart is more complicated because now we have only one tape. We have to move back and forth with our tape to read the input and to write correct results in designated spots. Okay, so let's see it running. Now this is the same, my simulator for Turing machine with only one tape. Over here, it's gonna record ones, and over here it's gonna record zeros, and over here is our input. So let's see how it works. You see the machine now has only one tape, so it has to move back and forth, and it's a little bit tedious. That's why we have multiple tapes to make it easier, but as you see, it works. So it's not a proof that they're equivalent, it's just an example that we can do whatever we want with only one tape. Okay, we're done. Okay, so Turing machine makes arithmetic awkward because it reads tape, it makes the decision, swaps symbols and swaps the symbols and moves tapes. It's a really weird math because it doesn't really increment the number, it just changes one number to the other, which is the same thing, but it's not really natural for us. So Turing machine is not the only computational model there is, there are others. And one that I found is math friendly, meaning it actually does its own arithmetic. It's called register machine. So this picture is a logo of Rodrego by Daniel Dennett, and it's a program that simulates register machine. So I will come back in a second to this picture because it pretty much shows you all the features of register machine. So let's look at the definition. So register machine is a machine with finite number of registers. Each register holds an integer bigger or equal 0. So instead of symbols, we have numbers now. We have actual numbers. We have control unit that execute instructions. And we have sequence of instructions. It's like actual program now. So what instructions do we have? We have only 3 instructions in register machine. Increment instruction that increments register R and goes to instruction K, and decrement instruction that decrements register R and goes to instruction K. So I told you that register can hold only numbers bigger or equal 0. So if we try to decrement but it's 0, instead of doing that, we simply branch. We go to instruction L. So this DEB is short for decrement and branch. This instruction is also sometimes called DEC, but DEB is the most classic abbreviation for this instruction. And the third instruction is the halt. Well, just like Turing machine, we want our register machine to halt eventually. Okay, so now let's go back to our picture over here. So this character over here is our control unit. It reads instruction and executes them. And these bins are our register that holds number. So as you can see, control unit puts marbles in those bins, meaning that it can only increment or decrement register by 1. Okay, so let's look at the example. So this is how a flowchart looks like for a register machine, because just like for Turing machines, we have flowcharts for these. And this simply adds content of one register to another register. So you can see this is like add in assembly. So let me go really fast through this flowchart over here. Alpha means starting point. Omega means end point, means halt. So first thing we do in this register machine is we decrement register 1. -1 meaning decrement DEB instruction register 1. And if we succeed, meaning register currently holds a number bigger than 0, we decrement and we go this way in our flowchart. So the next thing we're gonna do is we're gonna increment register 2 and then increment register 3, and then we go back. And as soon as we hit 0 in 1, we go this way in our flowchart, and we're gonna decrement register 3 and increment register 1. So the point of this is that as we decrement register 1, we store the value in both registers 2. That's gonna accumulate because it really might have some number inside of it. And we're gonna hold a copy of register 1 in register 3. So we can later, in this second stage, restore it. So this is how program for a register machine I just showed you looks like. So let's run it. I also wrote a simulator for a register machine. Okay, so let's look at the example. So this is my simulator for a register machine. We have this program over here. This symbol over here indicates which instruction is currently executed. And we have 3 registers over here, 2010 and the third one, which is our buffer 0. And we're gonna add 20 to 10. So let's look at this. So as you can see, we're incrementing register 2 and decrementing register 1, and we're storing contents of register 1 in register 3 as well. So we're done with incrementing register 2, and now we're restoring register 1. 20, 30, 0. Looks about correct because 20 plus 10 is 30. Okay. So let's do something more complicated. We're gonna raise R1 to the power of R2, and we're gonna store our results in R3. So let's see how it works. So we need 6 registers to perform this operation. We will raise 5 to the power of 3. This register machine is gonna execute pretty fast because this operation might take very long time otherwise. So we're done. So 5 to the power of 3 is 125. So it appears to be working, but it's still pretty slow despite its usefulness. And the question is register machine more powerful than Turing machine? So I think most of us should already know that no, it's not. They're equivalent. And why? We can refer to Turing Church thesis that says a function on natural numbers is computable if and only if it is computable by a Turing machine. So the only problem with this thesis is what computable means. And informally, how Turing referred to a computable function is that you can take a human, give him a pencil and paper, he's gonna compute the function eventually. If he can do it, then Turing machine can do it.